Hi everyone, my name is Paul, and I'll be talking about the physics behind the p-n junction, as well as how it explains the operation of a solar cell. In this presentation, I'll be covering the topics of the band structure of semiconductors, intrinsic and doped materials, and the motion of electrons and holes within a semiconductor. I will then introduce the p-n junction device and tie it all into how a solar cell operates. Now, for this presentation, I'm going to be covering some of these topics very briefly, but I'll be providing references so you can do some reading after the presentation. Now, before this presentation, you should be familiar with the basic concepts of semiconductor physics, such as the band gap of a semiconductor material, as well as how electrons and holes will behave within a material. So to start, I'm going to briefly cover semiconductor band structures. So for real materials like gallium arsenide, we have a relationship between energy and momentum of an electron. And you can see that these relationships are quite complex. So what we can do is we can approximate this using a parabolic structure, which will look like so in this middle figure. We'll have a conduction energy band and a valence energy band. And a very important concept is, of course, is that we end up with a band gap of forbidden energy levels, which is one of the unique properties of a semiconductor. Now, these conduction band and valence bands are governed by these parabolic relationships, and you can find a lot more detail on this in chapter 3 of Streetman. So the next thing we need to do is we need to derive the density of states for different energy levels in order to figure out how electrons will occupy the conduction and valence band. Now, this can be calculated for a 3D crystal with a parabolic band structure, and this is shown in Appendix 4 of Streetman. The result is shown in this equation here and shows energy versus the density of states relationship, which takes on a square root relationship. Now, once we have this density of states, we now need to figure out how electrons fill the density of states. And what we need to do is we need to look at Fermi-Dirac statistics. Now, to figure out how electrons will occupy these states, what we need to do is we essentially count the number of ways a number of electrons can be arranged within a number of states, which is the density of states from the previous slide, subject to the Pauli exclusion principle. And all of this can be found in Appendix 5 of Streetman or Chapter 3 of Newman. The result is this fairly simple equation with a very important parameter called the Fermi level. Now, this Fermi level is defined as the energy level at which the probability of occupancy is about 1/2. Now, for this equation at temperature of 0 Kelvin, we'll notice that for energies above the Fermi level, we'll have no chance of occupancy. So that means all the electrons will occupy energy levels below the Fermi level. As we increase the temperature, you notice that the tail end of the distribution will reach further and further into higher energies. So that means at higher temperatures, we'll be more likely to see electrons with a higher energy. If we superimpose the Fermi-Dirac distribution with a band structure of a semiconductor, we'll have the conduction band and the valence band, and the Fermi level will be exactly in the middle of the semiconductor band gap. Now, at 0 Kelvin, we would expect no electrons to occupy the conduction band, but all the electrons to occupy the valence band. However, once we start increasing the temperature, the tail end of the Fermi-Dirac distribution will extend above the conduction band, so we'll expect a small number of electrons to be in the conduction band, similarly a very small number of holes to be in the valence band. Now, in order to change the distribution of carriers in a semiconductor, what we can do is we can add dopants. So we have two types of dopants, which are essentially impurity atoms, which are inserted into the crystal structure of a material. And we have N-type and P-type dopants. N-type dopants are atoms which provide donor energy levels really close to the conduction band, and they can provide an electron with very little energy. Similar P-type materials will have atoms which have acceptor energy levels very close to the valence band. Now, at 0 Kelvin, we would expect no electrons to occupy the conduction band and no holes to be in the valence band. However, once the temperature increases, we would expect the donors to become activated, and the electrons will jump up from the donor states to the conduction band, providing lots of electrons in the conduction band for the N-type dopant. And for the p-type dopant, we'll have electrons from the valence band jump up to the acceptor levels and activate those dopants, leaving lots of holes in the valence band for conduction. If we now look at our Fermi-Dirac statistics and superimpose the Fermi-Dirac distribution with our two cases of the p-type and the n-type material, the Fermi level for a p-type material will be very close to the acceptor energy level, and we can see that the tail end of our distribution is very small in the conduction band, so we would expect very little electrons to be here. However, for an n-type material, the Fermi level is very close to the conduction band, and we'll expect lots of electrons to be here. So what we can do is, by inserting these atoms into the semiconductor crystal, we can control the population of electrons and holes within the material. So now I'll talk about the motion of electrons and holes. There are two types, and the first type is what happens to electrons and holes when they experience an electric field. Now, under no electric field, electrons and holes are expected to bounce around randomly within the material, and there will be no net displacement. Under an applied electric field, this random motion will also experience an applied force in the direction of the electric field. So then, after many bounces, our electron or hole will be displaced a certain amount. Now, this is called the drift of the electron in a field, and is often referred to the drift current. It's expressed here in this equation, with Q being the charge of the electron, N is the density of electrons, mu as the mobility of electrons, and E the applied electric field. The other type of motion is diffusion, and diffusion is when electrons or holes will want to move away from a high concentration into a low concentration. So as long as there is a gradient of concentration, there will be diffusion current, and it's governed by this equation. For example, if you have a large amount of electrons somewhere at x equals to 0, after a certain amount of time, they'll diffuse away from each other. And the longer we wait, the further they'll diffuse away from each other until they're evenly distributed. So that's just one example of diffusion current. So now that we have some of the basic concepts down, I can introduce the concept of a p-n junction. A p-n junction is a very useful device and consists of a p-type material connected with an n-type material. So let's see how this works. So we'll start with a p-type material which has extra holes, and an n-type material which has extra electrons. When we bring this together, what's going to happen is that we're going to have a large gradient of concentration. So there'll be lots of holes here and no holes here. Therefore, the holes will want to diffuse over. And similarly for electrons, there's a large number of electrons here, but very little over here. So there'll be diffusion forces driving electrons across and holes across. So there'll be hole diffusion and electron diffusion. However, this cannot continue indefinitely because electrons and holes, they will leave their activated dopants behind. So there will be negative charges in the fixed in space in the p-type material, and positive charges fixed in space in the n-type material. So there will be this built-in electric field set up between the n and the p region. So this is what's going to counteract our hole diffusion and electron diffusion. There will be hole drift and electron drift. Eventually, once steady-state equilibrium is reached, we'll have a so-called space charge region or depletion region. What we have is all these activated dopants on the p and the n side with a built-in electric field, and any free carriers will be swept across to the p or the n-type region. So now it's important to introduce the concept of minority and majority carriers. So for p-type material, what we have is we have a lot of holes in the valence band, but very little holes in the conduction band. So the holes will be called the majority carrier, and if we have some sort of event, optical or thermal, which promotes an electron from the valence band to the conduction band, this electron will be referred to as the minority carrier. Similarly, for the n-type material, we'll have lots of electrons in the conduction band, so this is the majority carrier. But if an event promotes an electron from the valence band to the conduction band, this hole is now the minority carrier. So this is a very important concept which we're going to encounter very soon. So now we're going to take a look at the band structure of the p-n junction. So we'll start with the p-n junction at equilibrium. So the p-type and the n-type material will have the Fermi level close to the valence band and the conduction band respectively. And when we join the two ends, we would expect them at equilibrium to line up with their Fermi energy levels. So this is what we would expect. And a very common way to draw this would be to connect the conduction band with smooth curves and the valence band with smooth curves. So what we'll have is we'll have a built-in potential from the built-in electric field, and majority electrons here, and majority holes here. Now, if we apply a reverse bias, and reverse bias is defined such that we add an electric applied field in the same direction as the built-in potential field. What we'll see is we'll increase the built-in potential, and we'll still have lots of electrons here, lots of holes here. And the depletion region is going to increase in size. Now, if we apply a forward bias, what we do is we subtract from the built-in field. So what happens is that the built-in potential is now less, and the majority carriers over here will have a chance to overcome the potential barrier and be injected into the opposite region and become minority carriers. So electrons will be injected across the depletion region into the p-type material, and holes will be injected across the depletion region into the n-type material, and they will become minority carriers. So this is a very qualitative description of a p-n junction. So let's see what relationships govern this process. So we talked about under forward bias how minority carriers are injected across the junction. So the carrier concentration on each side is given by these two equations. And this derivation can be found in Chapter 8 of Newman. But essentially what we have, if we have a p and an n side, we have some sort of equilibrium concentration of minority electrons here, and we have some sort of injection level NP. Over here, we have a minority electron concentration on the n side, hole concentration on the n side, with the injection of holes, minority holes. So after these carriers are injected, they'll travel through the material, and this is governed by the ambipolar transport equation. And this can be found in Chapter 6 of Newman. But to summarize the discussion in this chapter, the resulting differential equations will govern how the gradient will behave over space. So to solve these two differential equations, we'll need to apply some boundary conditions. So the two boundary conditions are such that at the depletion region boundary, we'll have the injected minority carrier levels, and far away from the depletion region, the minority carrier concentrations will be reduced back down to the intrinsic levels. So if we do all this, once again summarized in Chapter 6 of Newman, we'll have the following two distributions. And the important part is that these two distributions are exponential decay functions away from the junction. Now that we have the gradient of minority holes, what we can do is we can plug this into our diffusion equation to figure out the diffusion current density. And then if we substitute this into the previously found concentrations, what we can do is we can find the minority hole current and minority electron current at the junction, which has this exponential component to it. Now, if we add this up together, we'll get the total current across the junction, and this is known as the diode equation. Now, there's a constant called the reverse saturation current, and if we apply a negative bias here, the current will eventually stabilize at the reverse saturation current, and there will be very little current going across the junction. However, under a forward bias, the current will increase exponentially. So this is the property of a p-n junction. Now, what I like to do is analyze what happens when this diode is diode is another name for a p-n junction. What happens to it when it's under illumination? So if we illuminate the junction with light, there will be an electron-hole pair generated. And if it's generated within the depletion region or really close to it, it will be swept across by the built-in electric field, and the electron-hole pairs will be separated. From here, the electron and the hole can be collected at the terminals, generating an electron current and a hole current. So this total current will be the photogenerated current, and it is subtracted, if you take a look at the signs, it is subtracted from the diode equation. Now, if we plot this, we can see the IV characteristics of a diode in the dark and under various levels of illumination. For a solar cell, this region is the region of interest. So if we apply a load resistor, what we can do is we can figure out what the voltage and the current is across this resistor. And the important characteristics are the, the short circuit current and the open circuit voltage. So these are some of the parameters that under standardized illumination can help us compare different qualities of solar cells. Also, we can draw a rectangle underneath this IV curve and the rectangle with the maximum area will be the maximum power point, which is the maximum current, maximum point current, and maximum power point voltage. Finally, for a solar cell, a fill factor is important, and fill factor is essentially, it tells us what this shape looks like. So if it's really close to a rectangle, it'll be close to 1, but if it's really close to a line, it'll be much smaller than 1. So this presentation has summarized so far the physics behind a p-n junction, and now that you see that a p-n junction is essentially a solar cell, you can do some more reading to figure out what affects these different parameters and how to actually use a solar cell for different applications. So I'm going to present some sources I used. So most of my information comes from the Newman and Streetman textbooks, so you can find them over here probably in a library. And also this website called pveducation.org. This is a very useful website which has a lot of discussion related to solar cells. Thank you very much for listening, and I'll be happy to answer any questions in the discussion.